the basic setup. Shows a more detailed setup with two possible scenarios. We have, with reference to A, an original problem that we will call the engineering problem, for example, determine drag and lift of a new innovative wing profile or the electronic configuration of a new molecule. The first step in the solution of the engineering problem is its transformation into a numerical problem, typically a linear system or an eigenvalue problem, that is solved by means of a well-known numerical algorithm in order to obtain a numerical solution. The final step is to use the numerical solution to obtain the engineering solution, that is, the values that are of interest for us, for example, drag and lift in the wing problem. It is worth to discuss in some details the three steps. A. Typical scenario: an engineering problem is converted to a numeric problem that is solved to derive the desired engineering solution. B. Outsourcing by encrypting the engineering problem, and C. Outsourcing by encrypting the numerical problem. Many engineering problems require the solution of differential equations that, when discretized, give rise, usually, to a linear system or an eigenvalue problem. The matrices obtained with the discretization can be quite large but, usually, sparse. Note that instead the engineering problem has usually a relatively compact description. In the example at hand, it would be a description of the geometry of the wing, by means of 3D model format, together with a description of the airflow. In the case of the molecule, it could be a description of the configuration of the molecule, for example, by means of its structural formula. Although intuitively one can imagine that the solution of the numerical problem is the heaviest part, even the discretization step can be non-trivial. For example, some discretization technique, for example, the popular finite element method, FEM, requires to partition the space using a grid whose generation can be fairly complex. Finally, it is worth observing that with large problems, not only the required CPU time can be a problem but also the amount of memory required that can become readily prohibitive because of the dimension curse. Indeed, many engineering problems involve at least 4 dimensions, 1 for time and 3 for space. This suggests that working with very sparse matrices, and preserving their sparse structure, is of utmost importance. This will be important in the following when talking about some proposals found in the literature. Finally, it is worth observing that there is a good degree of arbitrary in the discretization step. If a grid is used, it is not uniquely determined. In finite difference method, FDM, the ordering used to map the grid points to matrix coordinates is arbitrary. In methods based on function space discretization, for example, Galerkin-like methods, there is a wide freedom in the choice of basis functions. This implies that while it is known how to go from an engineering problem to its numerical counterpart, it is not clear how, or if, it is possible to go in the other direction. This is important in our context since we can expect that the opponent will be interested in the engineering problem rather than in the numerical one. In this step, the numerical problem, typically, a linear system or an eigenvalue problem, is solved to give the numerical solution, typically, a vector. If the problem is very large, this step can be very CPU consuming. Algorithms used for the solution typically exploit the very sparse structure of the matrices involved. For example, in the solution of a linear system, usually an iterative procedure is preferred, since the iterative procedure exploits more easily any sparsity. The cost of a product matrix vector is proportional to the number of non-zero elements, while the inverse of a sparse matrix is not necessarily sparse, requiring much more memory and CPU time to be handled. This suggests that if the encryption is applied at the numerical problem level, see section 3 in the following, care must be exercised in order not to spoil the sparsity, although this goes against with the requirement, sometimes stated, of hiding the number of zeros, see section 4.1.1. This step usually is not as computationally demanding as the previous ones. It amounts to extract from the numerical solution the values of interest, for example, drag and lift in the wing example, or producing suitable visualizations of the data, for example, in the electronic distribution of a molecule example.